Welcome to this deep dive into the automotive automation testing fundamentals. Today, we are exploring the critical bridge between manual test cases and automated ECU validation. As vehicles become increasingly software defined, understanding how we automate the testing of these complex systems is essential for any engineer in the field. Before we begin, let's look at our journey today. We'll start with the fundamentals and the limitations of manual testing. Then we move into the technical architecture of automation. We'll look at real world ECU examples, best practices, and how to decide which tests are right for automation. By the end of this session, you will have a clear blueprint for modern automotive validation. At its core, automotive automation testing is the use of software tools to execute test scripts that verify the functionality of vehicle components, particularly electronic control units or ECUs. Instead of a human operator manually changing inputs and recording outputs, we use automated scripts to interact with the hardware and software, ensuring the system behaves exactly as designed under various conditions. Manual testing is very important for initial exploration, but it has limits. It is generally time consuming, prone to human errors, and nearly impossible to scale beyond. When you have thousands of software requirements to verify, we need more resources. In a modern vehicle, a single update might require retesting hundreds of functions generally. This we call it as regression testing. It is where the manual methods often fail to keep the pace with rapid development cycles usually. In the automotive world, automation is applied across the entire V model. It's used in unit testing for individual code modules, integration to see how software components interact with each other, and most importantly, in the hardware in the loop environments, sometimes SIL also. Here we simulate the entire vehicle environment to test the ECU's logic without needing a physical car on the track. The workflow follows a logical sequence. It begins with a clear manual test case in the hand. Engineers then convert these steps into a machine readable script, their own language they'll use. This script is executed by an automation tool, which sends signals like CAN messages or voltage changes to the particular ECU. The system then automatically compares the actual response against the expected results in the test case and generates a detailed report that anytime we can view. A robust architecture is what makes automation reliable here. It typically consists of three layers, as you could see. The test script layer, where the logic lives, the test engine, which manages the execution of these scripts, and the interface layer, which allows you to communicate with the hardware. This separation ensures that if the hardware changes at any point of time, right, you only need to update the interfaces. Not every single test script is need to be changed. Moving on, a standard framework provides the library of functions we use every day in test automation. It includes tools for diagnostic communication. It includes for CAN or FlexRay or LIN communication or the bus monitoring and report generation at last. By using a standardized test automation framework, engineering teams can ensure that scripts are reusable across different vehicle platforms, different products, which significantly reduces long-term development costs. So you are saving here. Let's look at a practical example. There is an ABS, you can call it as anti-lock braking system. Instead of a driver hitting the brakes on an ice, an automated script simulates wheel speed sensor losing the traction. This kind of situation it can simulate. So the script monitors the ECU's commands to the brake valves, measuring the response time in milliseconds. This milliseconds observations and all we cannot do in manual testing. So automation testing helps here. This level of precision and repeatability is simply not possible with manual testing. The benefits are clear: efficiency and repeatability. Once a script is written, right, it can be run thousands of times at no extra cost. This allows for continuous integration and continuous deployment. You can call it as CI/CD, where every time a developer changes the code, his side, the automation suite immediately checks for bugs, leading to much higher software quality here and faster time to market to the customers. However, automation is not a silver bullet. You can say like that. It requires a high initial investment in tools and skilled engineers. It's also not suitable for tests that require human intuition or for features that are still changing repeatedly or rapidly. So imagine there is a website. Usually the users will do checks that are like they want aesthetics, they want colors like that, right? That cannot be brought using automation. That cannot be verified using automation like that. If the system is unstable, you'll spend more time fixing the automation scripts than actually finding bugs in the vehicle software here, not automotive field. So how do we decide here? We automate tests that are repetitive, high in risk, or that require the complex data sets. These are the places where we do automation. We keep testing manual when it actually involves the human machine interface field, the field. Subjectively, if you think it's derivable assessments, uh, then we use automation, or one-time exploratory checks. There we use manual testing, right? So a successful validation strategy always balances these two approaches. So you don't just go for automation or just manual. Just it's like both combination we do. To succeed, follow these industry standards in automation. Prioritize your test cases based on risk. Ensure your scripts are modular and easy to maintain for long term. And always keep your test environment synchronized with the ECU hardware version. If your setup is outdated and your products are changing, you will be in risk. Most importantly, ensure your automated test reports are providing a very clear, actionable data for the developers to understand. To wrap up, automotive automation is essentially for managing the complexity of modern vehicles. It moves us from manual verification to scalable, precise validation. By building a strong test automation architecture and choosing the right tests to automate, we ensure that the vehicles of tomorrow are both safe and reliable. Now that you understood the fundamentals of the automation, how do we actually going to work in the automation frameworks? Then in our next video, we will explain about CAN bus, not just CAN protocol, but we are going to explore the CAN bus and the interaction with other ECUs, how it will happen. Thank you.